Okay, it's a great pleasure to be here. I think I'm more than 11 years overdue to be in Technion, and Haifa for sure. So this is a short talk. I will go through these relatively quickly, but if you want more of this, I think I'm giving a 5-hour-long lecture series on Wednesday. I'll talk about the main memory system, which is a critical component of all systems that we design today. And this system must scale in many dimensions: size, technology, efficiency, cost, and algorithms we use to manage it if you want to maintain the performance growth and technology scaling benefits. And this system is a bottleneck in any device that you put next to it: processors, FPGAs, GPUs, any kind of heterogeneous combination of them. You're bottlenecked by that link over there. And this is another view of the system. I won't belabor it, but basically, if you look at this, most of the system is really dedicated to storing and moving data. Only these little red components are the computation units, and even in those red components, most of it is really dedicated to moving and storing data today. So the question is, are we designing the right systems to facilitate movement and storage of the data? This is a very quick overview of the talk, but I will talk about some recent technology, architecture, and application trends that lead to some new requirements and that exacerbate some old requirements from the system. And I will posit and hopefully show you that DRAM and memory controllers, as we know them and as we design them today, are unable to satisfy these requirements. And there are some emerging memory technologies that happen to be non-volatile that enable some new opportunities. Unfortunately, I won't get to talk about all of this, but if you want the full thing, the 5-hour lecture is the thing. So given this, I believe we need to rethink the main memory system to fix the issues we're having with DRAM and to enable emerging memory technologies, while satisfying all of the requirements, of course. So this is a very quick outline of the talk. I'm not going to cover all of this, but I'll talk about the major trends, and I'll pick and choose 2 issues affecting memory related to the memory scaling problem. And hopefully these will be examples of these new memory architectures and enabling of emerging memory technologies. And we won't, unfortunately, get to the principles, but if you're interested, we can chat. So this is in one slide, the major trends that are affecting main memory as I see them today. Basically, we need more capacity, more bandwidth, more quality of service, more predictability out of the memory system. Energy and power is already a key system design concern, and DRAM technology scaling is ending. What is driving the capacity, bandwidth, and predictability requirements? Basically, we're putting more agents into the system. Applications are becoming increasingly data intensive, and we want to consolidate more and more. And this is one example of the memory capacity gap. Basically, as we put more cores into the system, we need more DRAM. The problem is DRAM capacity is doubling more slowly than the core count or the agent count. If you don't believe the core count, think about the computational power in terms of flops that you can process. And memory capacity per core is expected to drop by 30% every 2 years, which puts a lot of burden on the software programmers who rely on higher capacity to get better performance or to get more features. And if you look at the memory bandwidth, trends are actually much worse for memory bandwidth per core, which I don't plot it here, but we can talk about it separately. The second key trend, energy and power, is a key system design concern. This is actually really old data from IBM's Big Iron systems. In 2003, IBM's Big Iron systems spent 40 to 50% of their energy on off-chip memory hierarchy. Today in GPUs, if you look at it, about 40% of the power is on the memory hierarchy, in DRAM especially, and that's true for mobile systems as well. So this trend has become worse. And one of the issues with DRAM is it consumes power even when it's not used because you need to periodically refresh it. And one of the benefits of emerging technologies is this could potentially be eliminated. It's not fully clear yet, though. On top of this, DRAM technology scaling is ending. ITRS, which doesn't exist anymore, has been projecting for a long time that DRAM will not scale easily below some circuit size, feature size. And they've been saying some nanometers over here. I'll put a number to X later on, but scaling clearly has provided many, many benefits. As we reduce the size of the DRAM circuit, we got higher capacity, lower costs, and lower energy. The problem is we're not seeing those benefits anymore. In fact, we're getting much other issues as we reduce the size of this X, if you will. So let me go into 2 key issues. Since this is a relatively short talk, I decided to focus the talk on 2 key issues that I believe are perhaps the most important. I'll talk about the security and reliability of future architectures and designing fundamentally energy efficient or more memory-centric architectures. And I think you have predicted my psychological background, if you will. So I'll motivate both of these with the seminal work that was provided by Maslow in 1943. Basically, before everything else, you need safety and security. If you don't have that in a future technology, then that's not going to work very well. I'm motivated with DRAM, but if you look at DRAM, this is the technology we've come to rely on for a long time. DRAM stores charge in this capacitor, and this access transistor and the peripheral structures need to be used to access that charge. The problem is this capacitor must be large enough for reliable sensing, and all of this peripheral circuitry, including the access transistor, must be large enough for reliability and low leakage. And basically, as you reduce the size of the circuit, both of these properties become very difficult to maintain. And this was the value that was assigned to X by ITRS in 2009. They said scaling the circuit below 35 nanometers is challenging. And they were right, actually. Even though we're today at around 16 nanometers or so, it's come at a cost. One example of this, we've done this study with Facebook. Basically, we've examined all of the memory errors that we've seen in Facebook's entire server fleet worldwide. And one of the takeaways is that as chip density increases, server failure rate increases. You don't need to know the exact values over here. I'd be happy to have a discussion about this. But basically, DRAM reliability is reducing. And at the large scale, this is impacting systems very much. So we've been studying this at the small scale also. We've built infrastructures to understand such issues. I'm going to give you some results based on these infrastructures. Basically, we wanted to understand the retention time and reliability issues of DRAM. And while doing so, we've stumbled upon one thing. Basically, you can predictably induce errors in most modern DRAM memory chips today. And I believe this is a prime example of the scaling problem that we are seeing with existing technologies. And if you actually look at the hardware failure mechanism, this can create a widespread system security vulnerability. So there's an interesting tie-in between reliability and safety or security. And I'll give you the story of DRAM row hammer very quickly. Basically, like any other memory, DRAM is organized in terms of rows. And if you want to access a row, you need to apply high voltage to the word line. And if you want to access another row after that, you need to close that word line, apply low voltage. Now, if you keep doing that, if you keep reading memory, activate precharge, activate precharge, activate precharge, activate precharge, enough times before the cells get refreshed in DRAM, it turns out in many DRAM chips, you get errors in adjacent word lines that have nothing to do with this word line that you're hammering or keep reading from. Basically, by just keeping reading memory, you're flipping bits in adjacent rows. Now, this is not good in terms of reliability. With the infrastructure we've examined and found that in most real DRAM chips you can buy today, you can actually induce these row hammer errors. And what is most, regardless of the company, more than 80% of the chips that we've tested are actually vulnerable to this row hammer problem. And this is a scaling problem because before 2010, you don't see these errors. After 2010, you see a lot of these errors. And all of the DRAM chips that we've tested that were manufactured between 2012 and 2013 are actually vulnerable to this failure mechanism. And what is worse about this is actually you can write a simple program that exercises at the high level. At a user level, you can induce these errors. So basically, this program ping-pongs accesses to X and Y. And if the chip is vulnerable, you cause errors. And this is happening because of electrical interference. We don't need to go into the details at the moment because we don't have time. But basically, cells are too close to each other. Right? And you can actually induce errors in real systems. There's nothing special about Intel and AMD, other processors. As long as you can access memory fast enough, you can induce these errors. And if your chip is vulnerable, DRAM chip is vulnerable. So it's a real reliability and security issue. And when we wrote the paper, we said that basically memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this. This is really fundamental for reliability and security. And we believe that you could actually take over a system by taking advantage of these errors. And while we were actually looking at that, Google published this blog post where they showed that you can exploit this row hammer failure mechanism to gain kernel privileges. I will not go over this in detail. It's a really beautiful systems and security engineering blog post. You can take a look at it. I've quoted it directly from the Google's blog post over here. These slides will be available so you can look at it. But basically what they did was they could take advantage of the bit flips, and they could induce bit flips in the page table entries of a user-level process by actually exercising memory using that user-level process. And they could gain access, write access to their own page table of that process. As a result, once you have write access to the page table, you can get write access to the entire physical memory, and you've compromised the system. So this is called the Rowhammer vulnerability in DRAM. My favorite example of this is if you would like to actually break into some place, you keep banging on the wall, and the perturbations that you cause by that banging magically opens up another door that you're really after. And this is actually some really beautiful, insightful comment someone made on Twitter related to Rowhammer. And later on, basically, people show that they can gain unrestricted access to the systems of website visitors by remotely enabling this attack using JavaScript. And there's a more recent beautiful paper in ACM CCS last year where they showed that you can gain control of a smartphone deterministically in many Android systems. And maybe there are other future security problems like this. So how do we solve the problem? I'm not going to talk about the solutions in detail. So Rowhammer specifically is an interesting problem. Apple's patch is to increase refresh rates, which is probably a good solution in the existing systems. But going forward, we don't want solutions like this because we actually want to eliminate refresh because it caused a lot of issues in system design today. But we don't want to be forced into the trade-off of reducing performance and increasing energy to solve such reliability problems. I believe we need more fundamentally reliable architectures going forward. So basically, a better solution direction is this. So how do we actually design this? I believe we need to predict and prevent such safety issues that we're having with emerging technologies, including old technologies as well. So this is a very quick overview of three things that I believe are important. First, we need to understand. This is especially important for emerging technologies. We need to have methodologies for failure modeling and discovery such that we can predict, based on real device data, we can predict such issues. After that, we need to architect, somehow have a principled co-architecting of system and memory, and we need to design and test. Basically, we need to have a principled design, automation, and testing to fix such issues. That's why we've been building such infrastructures. We have such infrastructures for Flash as well. But there are two other, and I'd be happy to talk about the emerging memory technologies. I believe there are two other solutions. One is new technologies, somehow find some technology that doesn't have these issues. I think good luck with that. I believe any memory, when it scales, it will have such problems, but I'd be very interested in ideas here. And I think there's another direction, which is embracing unreliability. Maybe we should say, we cannot design all memory that's scaled to a very low dimension to be reliable. So why don't we have both types of memories? Maybe most of your memory is unreliable, but we should take advantage of it well. I think regardless of the solution direction, we need co-design across the hierarchy, all the way from devices up to the algorithms. And maybe problems at some point, but I don't know how to do that yet. So I think one challenge that I would like to emphasize is fundamentally secure, reliable, and safe computing architectures going forward. So this slide I'm going to skip. I think this is a more general solution direction, which I've already discussed. But basically, I'd like to reiterate that we need cooperation across the stack to enable some of these solutions. Now let me move into the second direction that I picked. How do we design fundamentally energy-efficient architectures? And I believe, by definition, these architectures need to be memory-centric or data-centric. We need to do computation close to data. And again, I'll motivate it with Maslow, if you will. Some people argue that safety and security are not the most important things, but everlasting battery life is the most important thing at the bottom, which may be true, actually, as it relates to safety and security at some point. So I think it's clear that regardless of what politicians may tell us, we need sustainable and energy-efficient future going forward. The problem is data access is the major performance and energy bottleneck. So our current design principles, unfortunately, cause great waste, in my opinion. Mainly because processing of data is performed far away from the data. And this has worked really well. This is not a new idea. Von Neumann architectures have been around for more than 70 years, actually. And they rely on three different components: computation, communication, and storage and memory. And so far, everything, actually, most of the design focus has really been on this computing unit over here. Today's computing systems are overwhelmingly processor-centric because processor is where the computation is really done. But this comes at great system cost. But the processor is heavily optimized and is considered the master, and data storage units are dumb slaves, and they're largely unoptimized, except for some that are on the processor die, the caches, basically. The problem is, it's still the memory stupid, basically. This is the Excites quote from NPR in 1996. And this is some data that I collected about 14 years ago. A processor, even though you have a lot of overlapping that happens in the system, most of the time the processor is stalled waiting for memory. So there are many perils of processor-centric design, in my opinion. I'll very quickly go over this. Basically, we have grossly imbalanced systems. Everything else in the system just stores and moves data. This is energy efficient, low performance, and complex. And we have an overly complex and bloated processor in the end, which is, again, energy inefficient, low performance, and complex. And this is a picture that I already showed you. Basically, most of the system is dedicated to storing and moving data. The problem is all of the trends are against this, basically. Data access is a major bottleneck today. Energy consumption is a key limiter, and data movement energy dominates compute. I will borrow a slide from Bill Daly from his high-peak keynote to motivate this. Basically, if you look at this 64-bit double precision floating point operation, it's about 1,000 times more energy efficient than a DRAM read or write. Basically, we're spending 3 orders of magnitude energy to move the data to do one arithmetic operation, a complex arithmetic operation over here. So is that a good idea? So I believe we need a paradigm shift to enable computation with minimal data movement, to do computation where it really makes sense instead of the processor, basically where the data resides, and make computing architectures more data-centric. So this is, of course, not an easy proposition. People have looked at this since 1960s, actually. The earliest paper that is not really fully analog is in 1970 by Harold Stone. But I think it's an idea whose time may have come, especially with emerging technologies. So we would like to enable an in-memory computation engine, and we'd like to query memory and get results and do more. Basically, there are many, many questions here which I'm not going to talk about. How do we design the compute-capable memory? How do we design the processor chip, the software interface, system software, and the languages, and the algorithms? And again, we need design across the stack over here. But I believe we need to start simple to enable something like this. And simple means not even computation. Even the data movement we're not doing right today, basically. All of this relies on data movement, data copy, and initialization. And even in large-scale systems, a significant amount of cycles are actually spent on memmove and memcopy in particular. It's not the data movement. Data movement is much higher than that. But the memmove and memcopy system calls occupy a significant amount of time. At the small scale, we're wasting a lot of energy if we want to copy one page to another page in memory. Basically, we're going all the way to the processor to do that copy. And we're basically doing 3 round-trip accesses to memory. This causes a lot of issues: high latency, high bandwidth, cache pollution, unwanted data movement. And with some technology, if you want to do this copy at 4 kilobytes, basically it takes this amount of time and this amount of energy. So wouldn't it be nice if we just had the option to tell the memory controller, please do the copy for me and don't bother anything else in the system? And this is an option, again. You don't have to do it all the time. In fact, doing it all the time is a bad idea, because you really want to decide where to do this. So this is low latency, low bandwidth, no cache pollution, and no unwanted data movement. And we have actually mechanisms where you can reduce this 1,046 nanoseconds to only 90 nanoseconds by doing this completely in DRAM, and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. We're going to exploit that row-level operation of DRAM. Basically, you need to activate the source row first, which brings the data into the row buffer. And then you activate the destination row, which basically connects the row buffer to the destination. And now you've actually got the data that you buffered in the row buffer and copied it into the destination row. Basically, by doing 2 consecutive activates in DRAM, you can enable very simple row copy. Of course, this requires data placement. Your data needs to be placed in the same subarray such that they share the row buffer. But if you're able to do that, you get a 90 nanosecond copy. If you optimize it, actually, it's only 80 nanoseconds. And this comes at a negligible hardware cost because most of the circuitry already exists in DRAM. So what's the benefit? If your data is placed nicely, you get about 11x latency reduction and about 74x memory energy reduction. And you can read the paper for more detail in terms of the system energy benefits. I'd be happy to talk about that. So going forward, we have actually support for in DRAM and or not and majority circuit that Nani talked about earlier. And this comes at low cost. Basically, you need to take advantage of the analog behavior of memory, DRAM, and you get 30 to 60x performance and energy improvements on these primitive operations. And I'd be happy to talk about that further. I believe new memory technologies enable even more opportunities, and there will be some talks related to this later on. I'm not going to talk about that. But I'll give you one more data point on utilizing 3D stacked memory to take advantage of in-memory computation to do in-memory graph processing. So if you look at large-scale graph processing, it's actually challenging. If you put more cores to it, you don't get that much performance. You get some performance. And it turns out this is actually a very memory bandwidth bottleneck problem. You have frequent random memory accesses and little amount of computation. Basically, you're really exercising that 1000x over and over many, many times in graph processing. So we've designed a system called Tesseract, which I'm not going to go into the detail of, but basically it takes advantage of this 3D stacked memory and logic layers, and we interconnect them using, this is like the hybrid memory cube, but we interconnect them using some interconnect. And each of the volts in this logic layer basically is augmented with a processor, specialized processor with message passing mechanisms. So it's programmed using message passing. It's an accelerator, and we have some specific mechanisms to do this as well. But let me give you some results, basically. We've compared this to existing systems. You need to change the programming model as well as the architecture to be able to do this. The end result is you can get about 13x performance improvement on a large number of graph processing algorithms. And why? Because you can actually take advantage of the large amount of memory bandwidth that's exposed to those cores that are underneath the memory. Out of that 8 terabytes per second, we can actually utilize about 3 terabytes per second, if you will. And the energy reduction, this is the entire system energy. It's not the memory energy anymore. You get about 8x energy reduction if you actually take this graph processing system. So I think this is just one data point. There's more to be discovered. But the challenge and opportunity for the future is we need more fundamentally energy efficient or data-centric computing architectures. OK, let me conclude, since you have up already. But I'll give you, I'll take 1 more minute to talk about someone else, a quote from a famous architect. Basically, people design architectures, and real architects design architectures based upon principle, not precedent. That's not always true, of course, but this is a quote from Frank Lloyd Wright. And instead of designing this, he designed a principled architecture, which is falling water. Right? I believe we've taken the precedent-based design far too long today, which is the von Neumann architecture. It's worked out really well, but we'll need to augment it with something else today. This is another example of the precedent-based design. It looks beautiful, nice, but it's certainly not like this. In my opinion, this is Stadelhofen in Zurich, and the architect is Santiago Calatrava, who also designed this Oculus. Now, don't talk about the cost of that Oculus, but basically, we'll need to design principled system architectures to solve the memory scaling problem. I don't think precedent-based architectures will work anymore. We need to discover design principles for fundamentally secure and reliable computing architectures, and design complete systems to be balanced and energy efficient, which means that they have to be data-centric or memory-centric, and enable new and emerging memory architectures that hopefully solve these well. I believe this can lead to orders of magnitude improvements, and I've shown you some little pieces of how to modify the system by very little and still get those orders of magnitude. And this can enable new applications and computing platforms and who knows what else. But I believe to enable this, we'll need to really think across the stack. We'll need to co-design potentially the devices with the algorithms over here. So, thank you.